I just wanted to take the opportunity to say a couple things. So I spent 3.5, almost 4 years at DARPA as the deputy director and then acting director of the science office. One of the people I had the pleasure of hiring was John Paskowitz. John came into DARPA as a program manager, and we were wrestling with this challenge of complex systems, complexity. And we spent probably 6 months looking at alternative ways to couch systems of systems design problem. One of the things the Department of Defense was wrestling with was the idea that, well, if I could, traditional military platform notion was to design a very exquisite system with very low failure rates, and they cost lots and lots of money. Why do that when I could maybe design an attritable system with lots of parts and lots of, lightweight or inexpensive unmanned systems, and maybe they fail 50% of the time. Maybe that's better in some case. What we realized was there was no actual mathematical vocabulary for doing this trade-off. Especially when you look at a complex organizational system of systems, and let's say certain capabilities are deteriorated, and I still want to achieve mission success. I want to understand this way a system could be dynamically reconfigured to achieve the functional outputs that my objectives would be for success. And we realized there was no mathematical techniques that people could model and understand these. So that's what's actually started DARPA looking at things like category theory, because in the Defense Science Office, the job of the program managers is often to take some phenomena that we think might be an ingredient in disruption and see if we can push it somewhere to transform a problem or provide some radical new insight. So Cascade was the first program which category theory showed up in. We were looking at essentially systems engineering, and I know we have a couple of Cascade performers here. The program has, of course, evolved over the time of inception based on proposals we got and then the work that's done and who the transition agents are. But I can tell you at inception time, one of the reasons category theory appeared in the call was we thought this might be a way of providing those insights in these complex dynamic worlds. Then we had another program where we were wrestling with not systems of systems in a military context or platform context. We were looking at it in the context of discovery, where we have different data sets coming at a scientist. Maybe it's data from a medical instrumentation, so I have some time series data. I may have records which are in a different form. I may have information from genomic data sets, and I want to somehow fuse these elements and visualize the way in which those data elements can be used to do data-driven discovery, design experiments, maybe even integrate the data. Well, there was a program we started called Simplex, which was simplifying scientific discovery, which focused on essentially the mathematical representation problem needed to look at integration of all the different data elements that are. And guess what? Kind of like whack-a-mole, category theory shows up again, right? And people doing things like topological data analysis, sheaf theory. This actually became an inside joke inside the agency that every program in DSO had to have a sheaf in it somewhere. But it was two very different domains, and suddenly we have people poking at the same issues, and we may have two people who have touched on the performer community from Simplex in here. That program has since ended. And then we had another problem, which was looking at problems in design and manufacturing, where we were trying to transform manufacturing into an information discipline. DARPA had spent an awful lot of money over the course of about 4 or 5 years looking at things like SysML. There was a program called Adaptive Vehicle Make, the idea of which was to create mathematical abstractions for manufacturing from this level all the way down. There was a huge effort in AVM on things like SysML. So AVM actually kind of sort of didn't work. There were things about it that turned out to be pretty good and things about it that failed. Namely, they couldn't build a system at the end of the day. And that's because there were abstractions that were missing. So SysML diagram way up here, well, 3D print which part? Right? I mean, well, how does this connect to the part, right? So we had certain levels of abstraction that the representation covered, and then certain other levels where there were complete gaps in the ability to design function, behavior, and integrate. So we developed a program to look at the new advances in additive manufacturing, because now, why would I sit down in front of my CAD system and draw dimensions and tolerances when I can actually specify function? I can specify some higher level behavioral or physical property, and then just let the machine, through physical simulation, derive the shape property that would then achieve that function. And it might not be just the discrete shape, but you could actually have mechanical behavior you could even derive. Now, a lot of the work we had been funding was in additive manufacturing for structural, but we wanted to get into things like multifunctional materials, heat transfer properties, behavior, multiphysics in the structures. So it turns out in that program, one of the challenges came about interoperability, trying to do mappings between different representations across different scales. I'm trying to represent material at the voxel scale, where I'm dealing with the melt pool in an additive manufacturing, E-beam or some other kind of electron deposition process, or I'm dealing with it in a material removal, or I'm dealing with it in a context where I'm doing something with laminates or composites. Well, guess what? Now I have to worry about material properties at the level of microns, where the feature sizes are really small, and I have to worry about behaviors that are the size of bread boxes and airplanes. So understanding how information flows up and down these physical regimes was something there was really no mathematics for. The way this is done now and is essentially, well, we have one system for which we do the atomic microscopy level modeling, and then we dump out a file and we try and translate that and read it into the next system and move things up a scale, and we're just translating files back and forth, and this is crazy. So we looked at a number of things in this program, which ended up being called trades, and one of the things that popped out was a serious effort among several performers to look at interoperability and perform it, so that you're not doing this traditional kind of von Neumann separation of computing and data. So again, ideas from category theory have shown up there. So what I find very interesting about this topic, and this is, I'm like 8 weeks out of DARPA, so you have to forgive me, you're part of my 12-step program as I return to doing actual scientific work instead of managing it. What I find fascinating is I think there are opportunities for applications. I'm looking for kind of killer apps. What things can we build with these mathematical techniques? I think there is a vocabulary of abstractions that all of these problems, whether you look at interoperability, whether you look at system-to-system design, there's a set of abstractions that we as human beings need to have access to design these systems, and the vocabulary doesn't exist right now. So what are these tools? And the analogy with programming languages holds that you don't right now write anything in machine code unless you build compilers. We think in higher level functions. So is something like category theory a way to get these abstractions, whether they be for designing mechanical systems, interoperating scientific data, or whether the abstractions are like systems? So what I'm looking for here myself is to essentially integrate with the performer community so I can become one again, and try and figure out where are some opportunities to build tools. I think this kind of workshop is awesome, so I appreciate doing that. So I'm happy to take any questions, but that gives you a little context of maybe why a couple things might have shown up at DARPA in 5 years.
What's the name of that manufacturer?
The program was called Trades, Transformative Design. There's a few people in that program. I see one over here who's I don't think you're working on that task, but we have people working on interoperability as essentially one of the enablers for new design paradigm. Right? Yeah.
I read the BAs, and I've noticed some of this DSO sort of, language percolating into STO and other parts of DARPA. Is that a conscious effort?
Well, I cannot say anything other than what we were trying to do when we were there. So I am no longer there, so it's a different management team, and they're all awesome. But DARPA changes with every generation of people who come and be program managers or on the leadership team. So I had my window, and there might be a little echo on some of the things we've done. But to your point, a lot of what you see come out of DARPA is driven by the people. And there were at least 2 people, one in STO and one in DSO, who were going back and forth a lot. And on the management side, I was also, I'd been a performer in STO actually before I came. So there was a conscious effort in DSO to actually look at the very disruptive scientific frontier that could enable new capability and do it in a way that didn't behold us to actually being yoked to some system. To look at the math, and if we're successful, then STO or some other office could then build something. So there was this conscious of, can we cast the stone far enough that then somebody else will pick it up?
I'm gonna have to cut it off.
All right,
Bill.
thank you. I'll be around. So.